In this video series, you can learn with me how to train your own LLM. So I'm gonna be coding and explaining everything, the code, the mathematics, the logic, so you can program and build and train your own LLM that's very small and cheap to train, only a few dollars or even for free if you want to wait a bit longer for it to train. So you can do your own research if you are a student, or you can even apply it in business possibly. Or you can learn how to become an AI researcher or scientist. Or engineer, of course. We will learn so much in this video. First of all, we will learn how DeepSeek implements rotary positional embeddings. So how they implement RoPE, the code step by step. You will understand it 100%. We will also learn how PyTorch stores and accesses memory and goes through memory in the GPU. So you will learn this low-level understanding that DeepSeek engineers have, and you will be able to program very fast models because of that. We will also make some adaptations of the DeepSeek code, so you will learn how to adjust and change DeepSeek code to suit your own requirements, and you will understand it so well that you will be able to change this rotary positional embeddings in this video and other parts of code in other videos as well. We will also learn how PyTorch compiles code, builds computation graphs, and optimizes it in order to be able to understand what we are coding now, this RoPE. By following this video and other videos in my series, you will be able to learn with me how to do AI science, AI engineering, how to code LLMs from scratch, and how to train our own LLMs. And also the main advantage of this video is you can self-learn. You can learn with me and see what I'm doing. You can also learn. So I'm trying to help you figure out what you need to learn. And I will give you in the description below URLs, links to these AI chats, to other materials that I'm using in this video. So you can also follow me, and anything you don't understand, you can ask AI and AI will explain everything to you.
So what are strides in memory, in GPU memory? Think of memory like a long hallway with numbered rooms. So these are memory addresses from 0 to 11 and data in each memory address. When you have a tensor with shape 232, PyTorch needs to know if I'm at position ijk in the tensor, because so this is a shape, so it has innermost dimension is 2, and then 3, and then outermost is 2. For example, this could be batch size, sequence length, and model dimension, or token embedding dimension. So PyTorch needs to know if I'm at position ijk, whatever that position is, in the tensor, which room number contains that data. So if I'm at this position, which memory address contains that data at that position? Strides are the answer. They tell PyTorch to move one step in dimension x, jump this many rooms in memory, so this many addresses. So dimension x could be, for example, any of the dimensions. But let's say it's this first dimension. So to move one step in this first dimension to the next element, we need to jump a certain amount of addresses to get to that next element, where that next element begins in the memory. So normal contiguous case. For a tensor with shape 232 stored contiguously, memory is 1, 2, 3, 4, 5, 6, and tensor is, you see, the first element stored the first place, second element stored at the second place, third element stored at the third place, and they are all together. There is nothing, like there is no some other data in the middle of this tensor. They are all stored next to each other in the memory. So each of the elements is stored next to each other in the memory. So the strides here would be the following: 6 to 1. So to go from tensor 0, 0, 0 to 1, 0, 0, so 0, 0, 0 to 1, 0, 0. So we are just going from the first element here to the first element, to the second element. So in this outer dimension, this is the first element, this is the second element. So this is element with index 0, element with index 1. So to go from 0, 0, 0, which is the first element of the first, so this one, to go to 1, 0, 0, we need to go 1, 2, 3, 4, 5, and then 6 to come, so 6 rooms to jump, 6 addresses. Jump 6 rooms. To go from 0, 0, 0 to 0, 1, 0. So this is 0, 0, 0. This is 0, 1, 0 because this is the second element. Yeah, so if you don't understand how, then I will leave you this URL below, and you should ask it to explain. This is for self-studying. Why is this? What is this one? What is this one? Why is it this one? Why is this one 0, 1, 0, etc. So then in our DeepSeek code, we have this view as complex command. So this will take pairs of numbers, so arrays of 2 numbers, 2 elements, and it will assign first number to be real number and second number to be treated as imaginary number. So I'm pretty sure they remain the same in memory. They stay as real pairs of real numbers, but PyTorch is now treating it as a complex number. So to do this, to pass this through view as complex, the innermost dimension must have 2 elements like this. And then we can pass it to view as complex, so this element will be treated by PyTorch as real and this as imaginary. So real and imaginary. So we need to, in order to use this, we need to have these pairs of elements. And they must be contiguous, so they must be next to each other in the memory. So that means that last dimension stride must be 1. So when we are traversing the last dimension, we must always just jump by 1, so they must be next to each other. Strides in every other dimension must be divisible by 2, because when you move to the next complex number in any dimension, you must land exactly at the start of a real imaginary pair. So we go these 2, then we can stride, and then, so if we look at the second dimension, this is the stride. It's this, and then this is the beginning, and then this is the beginning of the second, and then this is. If we look at this first dimension, then this is the beginning, and then this is the beginning. So the stride here is 6. And so for each of these strides, they are all divisible by 2, except the last one, the innermost dimension, which should be exactly 1, as I said. So they are divisible by 2, so we can move 2 by 2, so we always land on the beginning, so the beginning of the pair. If there are any gaps in your understanding, you can just ask AI. I will leave this below for self-studying. I expect you to be self-studying this mostly, and not it's difficult for just a YouTube video. So I had a bug in my file here where I'm trying to program from scratch some of the DeepSeek's multi-head latent attention parts and train some model. So this view as complex, as I said, the strides were not proper, so there were some bugs. So in order to detect those bugs and prevent them, I just created these checks that will log errors if there are bugs. So there are 2 types of checks. As I said, the last dimension. So the last dimension stride must be 1. So if xReshaped.stride of the last dimension is not 1, then throw error. And also every other dimension except last. So for I in range, so from 0 to the next to the last dimension, so last minus 1 dimension, we will check if it's stride of that dimension, each dimension, is divisible by 2. If it's not, then we throw an error. So I can see this in console and then fix it. So what I will do now is I will just stage these changes, quick commit message, commit and push. And then I will pull my changes and then let me run this again. So this is the model training. Now I have yet to get it to run, so it has some errors. I implemented DeepSeek's attention mechanism, DeepSeek V3 multi-head latent attention, into this LLM that I was doing. So we have some issues here. So this is interesting. It looks like this does not throw the error, meaning that when it checks these conditions, the strides are good. But when the PyTorch code gets converted into machine code, gets compiled, the compiler throws the error that the strides are not good. So these, my prints, don't throw the error, my checks, but the compiler throws the error, which is weird. So let's see what happens. Eager execution versus compiled execution. Your print statements and if conditions they are in would execute as expected if you were running your model in PyTorch default eager mode, i.e. without torch compile. In eager mode, Python code is interpreted line by line. Torch compile changes this. It first traces your Python code to build a computation graph, an FX graph. Then it hands this graph over to the backend compiler, in your case Inductor, to generate optimized low-level code. Okay, so this is what it does. A Torch compile, instead of going line by line, it will simulate all the function calls, create a graph of execution, which function calls which, what happens where, which variables go where. And then it will, once it has that graph, it will optimize it. It will send it to this induction, I forgot what the name was. And then it will maybe merge some kernels, it will change the code, it will optimize it. So maybe because of the changes made there, we get these stride errors in this optimization by Torch compile. And again, you can self-study this, so these videos are for self-studying. If you have any questions about this, you can ask ChatGPT, and then you can maybe follow me or ask ChatGPT anything you don't understand or want to learn more or are curious about. The role of tracing and fake tensors. During the tracing phase, Torch compile, specifically the component called Dynamo, might execute parts of your code with fake tensors. These are special tensors that carry metadata like shape and d-type, data type, but don't hold actual numerical data. So during the phase where the Torch is trying to figure out the computation graph, which function calls which class calls which, it can use these fake tensors that don't have any data, they just have hold information about shape and data type. Okay, it's possible that during this tracing phase, the fake tensors representing X reshaped do not have the problematic stride configuration that would trigger your print statements. So these conditions, X reshape, so these conditions might evaluate to false for these fake tensors, meaning that there is no error. So yeah, I'm a bit confused as well. Maybe I was wrong. Maybe during the compilation there was no error, but during real execution there is error or something like that. I'm not sure where the error comes from. But okay, for now we know that these fake tensors might not have this stride problem. Error originates in the backend compiler Inductor. The error message you provided clearly indicates Torch Dynamo execution, backend compiler failed, backend Inductor raised, runtime error, tensor must have a stride divisible by 2, etc. This means the error isn't happening during the Python level tracing, where your print statements are live. I feel like Gemini is making some error sentence structure, grammatical mistakes. I don't know why. So error isn't happening during the tracing, but I would suppose that my print statements would also work like during the actual execution, not just during the building of the computation graph, the optimizations and stuff. So instead, it occurs when the indicator backend takes the traced computation graph and tries to compile it into optimized kernels. Tries to compile traced graph into optimized kernels. Okay, we need to remember this. Inductor has its own set of rules, assumptions, and checks when generating code. It's at this stage that the stride requirements for operations like attention, view as complex default, used by Torch, view as complex, or the resulting tensor from attention, view as real, are rigorously enforced. If an intermediate tensor within the representation inductor is working with violates these stride rules, indicator will fail. Gemini making some grammatical errors. Yeah. Why prints don't see the error? The Python print statements are part of the high-level model definition. They are not part of the low-level code inductor that the code inductor generates, nor are they typically executed during the backend compilation process itself in a way that would reflect inductor's internal state, nor are they typically executed during the backend compilation process itself. So print statements cannot print inductor's internal state. So we cannot check the strides if the strides are good with in the inductor with print statements. The specific tensor and its stride configuration that the inductor finds problematic might be an internal representation within the compiler, possibly after some graph transformations or operator fusions that are not visible at the Python level where your prints are. Okay, let's go. Now I understand. Operator fusions. Complex number support in inductor. The warning, Torch inductor does not support code generation for complex operators. This is weird because I just copied this code from DeepSeek v3 code. Performance may be worse than eager. Okay, so it just doesn't support maybe optimizations. Okay, so this statement is highly relevant. This suggests that inductor's handling of complex numbers might be less mature or might involve internal decompositions or complex operations or into real ones. Gemini, grammatical errors, sorry. Such decompositions could inadvertently create intermediate real tensors with stride configurations that then fail to the checks when view as complex or view as real are encountered in the graph. So I guess the inductor could change complex operations into real operations, which would then change these tensors while in the graph during these operations. So in summary, the failure is a compilation time error within inductor, not a runtime error in your Python code that the print statements would catch in an eager execution context. And I will ask, so how do I find root cause of the problem and how do I fix it? So now that I understand this, that we read this, I actually found the same issue on GitHub. Here I just Googled striding problems with Torch compile, and somebody was implementing this PyTorch llama or something model, and they got the same issue. So I gave this to the Gemini, and it just suggested by reading the issue for me to call .contiguous after this reshape. So let me accept this. So I'm trying to run this to check if the problem is fixed, but I wouldn't be so optimistic because most of the time the problem is not gonna be fixed. only rarely you fix the problem, so we're gonna have to try more. And I don't even understand exactly what I didn't read everything, so but let me first check. If it works, if it doesn't work, we will understand it anyways. It looks like we still got the error, but maybe this time it's at a different place. Maybe we fixed it at the previous place and now it's a different place that we also need to fix. So I copied this error. So here, you know what's weird is that now this line that it's reporting the error, this line is actually after, so it's this line here. But before, I feel like it was, the error was here. So now it's here. So maybe we fixed it here. I'm not sure. So I asked Gemini if this is the same error. So let's see what it says. This is essentially the same underlying error related to tensor strides and complex number operations, but now it's being reported during the backward pass. View as real backward 0. Oh wait, no, not there. Don't look at that. Do not look at that. It's right here. View as backward real backward 0. So here is what this new traceback means. This is the same thing we have. The tensor strides must be divisible by 2 for all but last dimension. So we already know that. But here, error detected in view as a real backward 0. This tells you the error occurred during the backward pass of the torch view as real operation. So when we are doing the backward pass, we have this y. So we have this first y. And then the next thing that we need to calculate is PyTorch internally sets up a backward function, view as real backward 0, to compute gradients for y complex when gradients for y become available. So because we are going backward, now we first have y, and then the next thing is gradients for y complex from gradients from y. The compilation of this backward part is failing due to the stride issue. So I'm not sure how it exactly got that this exact thing from y to y complex gradients is the issue from this whole line. But let's read further. Because we can also now separate this into multiple lines. Maybe that way we will understand it better. Be able to trace better. Traceback of forward call that caused the error. So even if the forward pass appeared to compile or run, perhaps inductor made some assumptions or deferred the check, the specific way gradients are computed and tensors are manipulated in the backward pass can expose these stride incompatibilities more directly. Here is what I will try. I will just decompose this complex line into multiple lines and one operation per line so we can see where the error is. So first we will make it contiguous, then view as real, then flatten, and then just assign to the y. Same thing. So because I'm gonna stage this commit, just a quick fix. I have too many commits, so I cannot write detailed messages. Another option we have is not to use this view as real and view as complex at all and code this multiplication manually. So we will try that if this doesn't work.
Hello guys, I will turn on my camera. So it's absolutely hopeless. Maybe there is a bug with PyTorch, but I think the simplest thing would be to just reprogram this function without using view as complex and view as real. Just manually do it. So I copied this into the new Claude 4 and just told it to fix this manually, do it manually instead of these two. And so it's doing it manually instead. And this is it. I did not check it, but let's check it now. I'm gonna just copy this into my code and then run it. So warming up kernels. The error, the bug was around here last time. We see that Torch inductor does not support code generation warnings. Tesla T4 does not support, but there is no our error that we are trying to fix. So this looks really good. Okay, I think there is no more that error. Okay guys, let's go. I've been struggling with this for like 24 hours now. And we have finally solved it. This whole video was about just understanding everything around this error. We figured out that the problem was some bug within the PyTorch with the view as complex and the view as real. So we just removed it, we coded it manually, and now everything works. So now let's just go through this code and understand it very quickly. It's gonna be so easy. ChatGPT explains it very well. Actually, you can get more context even from this video. You can just look for this video on my channel, but let's begin. So X is the input tensor, batch size, sequence length, dimension. Frequencies is a tensor of pre-computed complex exponential values used to rotate the position dependent components of X. So explained in this video. Then we save the D type and we say X is equal to X float. This is Y, so rotary embeddings involve sine cosine operations and are generally applied in floating point precision. So F float 32. Purpose of D type, to restore the original type, float 16 or B float 16 at the end if needed. Then we need to reshape for complex arithmetic. So X reshaped, we get X view. And I think I explained this before. So the first dimensions will be the same all until the last dimension. And then the last dimension, we will split it into 2 dimensions. So now the last dimension will be just 2. And then the previous to last will be whatever is left. Because if we have here X last dimension 6, if we split it into 2 dimensions, then now the new last is 2, then this one will be 3. So 3 times 2 is 6. And so we will split the real and imaginary parts. So what does this do? Select the real part from the reshaped tensor X reshaped. So example, if you just do this, it selects the first element in each pair. So what do the 3 dots mean here? The 3 dots in PyTorch and NumPy indexing is called the ellipsis. It's a shorthand that means include all dimensions up to this point and only index the last ones I specify explicitly. So it will copy the all dimensions, batch, sequence length, and other dimensions. And here it will just take the first index of the first number with the first index 0. So it will be imaginary, or sorry, real part. So this takes all preceding dimensions of X reshaped as is, and from the last dimension, which has size 2, which is the pair, take index 0, the real part. So it will create a tensor, a tensor which will just have these real parts. Let's say we got this x.reshape.shape is this shape, then x reshaped and then 3 dots 0 returns a tensor of shape 2, 128 and 64. It slices like this, so all elements along the first 3 dimensions like this, and just index 0 from the last one. So you see, now it has 3 dimensions, but it had 4 dimensions. So even like the last dimension is now cut. So because each of these 64 elements previously had 2 elements, but now it just has 1 element. So we don't need to put that 1 element into a separate brackets, separate dimension. We can just put that 1 element into that dimension directly, because we just have 1 now. Then it will match frequencies shape with X. So it will add this batch dimension and add this new dimension here. Then it will select the real part and the imaginary part and separate them. So reshaping frequencies ensures it broadcasts correctly across batch and head dimensions. The new shape is 1 sequence length 1 head, dimension over 2, assuming it needs to match x real and x imaginary. Frequency is linear and frequency is imaginary. Hold the cosine and sine components respectively. I explained in this video that I will link below how to calculate these rotations. So cosine of the x is the real part and I times sine x, so sine x is the imaginary part. But you can watch it here, or you can ask ChatGPT and self-study to explain these parts, sine and cosine. So this is the manual complex multiplication. I explained this as well here. So this is how you rotate a vector. If you have a vector x, so x real, x imaginary, you wanna multiply it. If you wanna, instead of doing a rotation matrix, you can also multiply with a complex number. But anyways, this is, I explained it in the video I showed. And then recombine and restore the shape. So result, real, result, imaginary. We stack them and flatten. What is so? Torch stack joins real and imaginary parts back to shape the beginning shapes and then 2. So we return back to this shape and then flatten -2. Flattens the last 2 dimensions, going from shape, you know, this number of pairs 2 back to just dimension. Yeah, we just reverse. We reverse this beginning part here. We reverse this. Okay, and then just back to the type, whatever it was, like BF16 or something. So I'll leave you this below as well. Thankfully, we fixed the bug. I was recording this for like 3 hours and I spent some time yesterday as well. So thank you for watching. Check out my video here. I'm gonna be updating this project. I'm trying to build some kind of small DeepSeek kind of model, maybe do some research on this multi-head latent attention by DeepSeek or some other architectures. We'll see, I don't know yet. But this will eventually be a very cheap to train LLM. So thank you for watching. See you tomorrow, probably.